we're going to look at two, not too difficult examples, but two of them to continue looking at directional derivatives. And the first one here is we have a function of x, y is x divided by y, and we do have a unit vector. This would be equivalent to having the vector -1, 0. We could think of that as going exactly 1 unit to the left if this was the top view. And then the meaning of the directional derivative is if it's positive, that means z would be increasing, and if it's negative, that means z would be decreasing. We'd be going down through the paper. So let's do the calculation. Oh yeah, and we're going to compare it to something else before we're done. That's just a little teaser for a plot twist later on. So here's our theorem. We do need a unit vector, which we have, and we need two partial derivatives, which we still need to get. The x partial derivative would be x, the derivative of x is 1. This is a constant, 1 over y. And let's see here. The y partial derivative is going to be -x over y squared, and if that was too fast, let's look at x times y to the -1 and do a power rule. You'll be here in no time. There's pause buttons for a reason. Stay active, be involved, and then you're learning. If you're watching, there's better shows to watch probably. Be an active learner here. So there is no point given, so let me provide coordinates of a point. I cannot start from here at 0, 0, so there was a mistake in that picture there, because if y is 0, we're undefined values. So let's choose a different point. What if we started here at the point 1, 1? If we do that, then this vector at the point 1, 1, I can get the details. If y is 1, that's going to be 1. And if x and y are both 1, that's going to be -1. So my directional derivative of the function at the point 1, 1 is going to be the dot product of this vector and my direction vector, which says from your point go 1 unit to the left. That's not a full diagram. That is just enough to help remind me what I'm doing, because the directions are going to be to calculate the directional derivative. So we have here -1, 0, and that dot product is going to be -1. Apparently, if I start at the point 1, 1 and I go left 1 unit, my z will be changing by going down 1 unit also. That's a directional derivative. Now here is what I'd like to compare it to. Since u equals -1, 0, isn't this just the same as the x partial derivative? I mean, isn't that what the partial derivative means? It's the slope in the x direction, and if I did the y partial derivative, it would be the slope in the y direction. I think that was kind of hinted at in a previous segment, and certainly by the book. Well, we can investigate that. The x derivative at the point was positive 1. They're not the same. There's a number of reasons for it, but a simple reason would be to say maybe the x derivative means we have to go in the positive x direction. And I'll tell you, if we do change this vector to be positive 1, 0, this would have been a positive 1. Literally choosing to go the opposite direction means you're going uphill or you're going downhill. If you're going down the hill and you turn around, then you're going up the hill again. Directions just weren't part of our slope calculation when we were in algebra back in the day. All right. Okay. Let's check out my other example. You're going to love this one. 3 variables. So we could just check the formula. The directional derivative in a particular direction at a point 1, 1, 1 is going to be the vector we get by making all the partial derivatives dot product the unit vector. Alright, this needs to be a unit vector. I'm not even trying to understand what the meaning of this problem is. I'm just trying to do the calculation, get the answer right, and get my grade and go. It's not really the hallmark of a learner, but sometimes we've maybe made some of these minor sacrifices just to get to survive through the week till the weekend. So I could go through and make this calculation, but I'd like to go through and find the unit vector first. I did not call this vector u on purpose, as I didn't want to confuse people. But we have a vector 2, 1, and 3, and the magnitude of that vector will be the square root of 2 squared is 4, 1 squared is 1, 3 squared is 9, square root of 14. So the unit vector, I'm switching back to my natural form of components, 2 over root 14, 1 over root 14, 3 over root 14. Magnitude is 1. That's what goes here. Alright, so you know what? I don't have these values yet, so let me just take a moment before I worry about filling in the blanks. I'm going to use this side of my paper to sort of just do computations. What is the x partial derivative? Well, derivative of x is 1. That leaves me with a z. There's no x here, so that's 0. There's no x here, so that's 0. If I were to do this calculation at the point 1, 1, 1, I will get 1. Alright. Now, you want to see where this is going? Well, the directional derivative has 3 components here, and the first component there is a 1. What's the y partial derivative? No y there, that's 0. Derivative of y is 1, leaving me negative 2z squared. Derivative of 3y is 3. At the point 1, 1, and 1, we're going to get negative 2 plus 3 equals 1 again. I did not intentionally write this problem to come out like that. I just picked some numbers that didn't seem too big. Said, let's go along for a ride. Z partial derivative. Derivative of xz is x. Derivative of this is going to be negative 4y z to the first. Derivative of 3y is 0 because it's a constant now. At the point 1, 1, 1, I have here Is that 1 minus 4? Negative 3. Finally, something a little bit different. Multiplied, I should say, dot product, my unit vector, 2 over root 14, 1 over root 14, 3 over root 14. And that dot product will be 2 root 14 plus 1 root 14 minus 9 root 14, negative 6 over the square root of 14. Now, again, because of years of maybe not the best intentioned training, I feel like I'm done. I feel almost successful. Hardly anyone in the world knows how to do these calculations. The problem is, hardly anybody in the world cares also. So there's no one I can brag to. So, square root of 14 is a little bit more than 3. So this is, around 1.5 or so. That's what this is going to equal, about 1.5. So what does it mean? So in 3 dimensions, z, x, y, okay? So let's suppose we go 1 unit in each direction. So we go here, we go up 1. So there's a point here in space. Now, from that point, I want you to aim in the direction of 2, 1, 3. 2 units in the x direction, 1 unit in the y direction, 3 units in the z direction. So maybe it looks something like this, and make a unit vector. What we're saying is that this number represents a 4th dimension. This is a 4-dimensional problem. So let me give you something tangible we can actually measure. Let's suppose we're somehow suspended in air here at this point. We're going to go this direction, and the 4th variable is temperature. This says if we go 1 step this direction, we're going to lose between 1 and 2 degrees of temperature for every step we take. We're losing a degree or almost 2 degrees of temperature. We can totally measure something in this 4th dimension. It doesn't have to be measured in a spatial sense. The 4th variable, if it was temperature, just take a step that direction, we are losing temperature. If this is positive, we would be gaining temperature. Try switching the direction to the opposite direction and you'll find that this is positive. It's really easy to verify that. And that would be an example of looking at 3-variable problem. We're not quite done. There's one more big punchline left, so stick around.